Today we want to build on what we did last week, and we will also go ahead. So today we shall be looking at capacitor lab, and in doing this, we will be expected that at the end of this meeting, the participants, I mean you students, should be able to understand the following as stated in our intended learning outcome. You should be able to describe what a parallel plate capacitor is. You should be able to identify relevant mathematical equations that describe capacitors. You are also expected to be able to identify mathematical relationship between capacitance of a capacitor and the charge that is stored in a capacitor. You should be able to understand how to conduct basic experiments by simulation, or now you can verify some of these theories of relationship between capacitance and charge. And lastly, you should be able to conduct experiment by simulation, how to verify the relationship between capacitance of a capacitor and plate separation. Okay? Now, having said that, I will quickly take you through this interface to show you what a parallel plate capacitor looks like. Hello? I believe you are all hearing me.
Yes, sir.
Yes, sir. I can hear you.
And you're following me?
Yes, sir.
Great. Now, having said that, if you look at the figure you have right before you, the figure simply shows you what a parallel plate capacitor looks like. I will continue with this, my presentation, and since you are following. Now, if you look at what I have on the screen, this is a battery, and this is a parallel plate that makes up a capacitor. Now, when you talk about parallel plate capacitor, it's usually made up of two plates that are parallel to each other, that are arranged in a parallel way to each other. What we have here, as you can see on the screen, we have the plate A, and then we have plate B. Plate A has a plate area of 100 millimeters square. While you can look at these plates, this plate can be considered as maybe a square or a rectangular plate, which has a length L and breadth B. So invariably, the area of this plate can actually be calculated using the popular formula you know for area of a rectangle, which is what? Length times breadth. Is that okay? So take note of that. That takes care of the area of a parallel plate capacitor. If the capacitor has a plate that is rectangular or square in nature, then what you will have as the area of that capacitor is length times breadth. And we also have the separation between these two plates, talking about the distance between plate A and plate B. In this case, the distance between this plate A and plate B is the distance we have from here to here. It's the distance you have from here to here. And based on this, you can actually express this as the separation between the plates, and is given as 10 millimeter. Is that okay? In this particular capacitor. Usually your plate A is equal to plate B, and like I explained, the area of the plate is given as length times breadth. Okay? Going further, we look at what a capacitor is. Generally, capacitors are used to store electric charges. And in reality, it's actually made up of two plates that are separated by a thin insulating material known as dielectric. So the separation between capacitor plates is usually made up of a very thin insulating material, and this is known as the dielectric. One of the plates of the capacitor is usually positively charged, while the other one is negatively charged. And so you have two parallel plates. One is positively charged, while the other is negatively charged. Okay? Having understand that, then let's go further and also look at the amount of charge that can be stored in a capacitor. The amount of charge that can be stored in a capacitor. Usually, if you remember the figure I showed you earlier, we have a battery that is connected to these parallel plates. When the potential energy from the battery is released into this charge, energy is bound to be stored in that capacitor. And the quantity of energy that is being stored is directly proportional to the applied voltage V from the battery. I take that one again. When you apply a potential from a battery to a parallel plate capacitor, there is bound to be a store of charges in that capacitor. And the quantity of charge that is stored is directly proportional to the voltage that is applied to that capacitor. And the constant of proportionality is given as the capacitance of that capacitor. I take that again. The quantity of charge that is stored is directly proportional to the potential that is applied to the capacitor. And the constant of proportionality is the capacitance of that capacitor, which is C in this expression. And so, where we are now, what we have now is the quantity of charge that will be stored in a capacitor with an applied potential, applied voltage V, is equal to the capacitance of that capacitor, which is given in farad, multiplied by the applied voltage. And the quantity of charge that is stored in a capacitor as a unit coulombs. And the symbol for coulomb is C. So the quantity of charge stored in a capacitor is measured in coulombs C. Okay, going forward, let's take a little deeper at this relationship that we have between charge and the applied voltage. And let's compare it with the linear equation that we looked at last week. If you recall from the lecture of last week, you should be able to remember this particular graph I have here. This is the normal graph of a linear equation, whereby you have your y-axis, then you have your x-axis, then you have the points joining your linear graph together. In this case, the intercept is 0. Hence, we have our y is equal to mx as the equation expressing this linear graph. If otherwise, you will have an expression like this: y is equal to mx plus c, where c is the intercept on y-axis, However, in this case, because intercept is equal to 0, your graph will pass through the origin 0, 0, xy. And having understood that, let's try to do a quick comparison of this equation we have. Q is equal to CV. If you look at this equation, it's comparable to the general equation of a linear graph. And so since it's comparable, we can actually do a one-to-one relationship and look at which of these can actually form our y-axis, which of these can actually form our x-axis. Remember earlier in the definition of, or the relationship we have for columns, sorry, the relationship we have for charge is directly proportional to V, is directly proportional to V. So we can say our Q is our y-axis, YV is the x-axis, and that is illustrated in this graph you have here. This is a graph of Q is equal to CV, where we have our Q on y-axis and we have our V in volts on x-axis. With this, the slope of this graph, will be C, because if you look at this place, C corresponds to M, which is slope in this place, in these equations. And so with this, we have the slope of this graph is equal to C, which is the capacitance of this capacitor. And it is expressed as change in what? Change in Q over change in V. Change in Q, the Q over the V. That is, the change you experience from this point to this point along y-axis, along q-axis, divided by the change you experience from this point to this point along v-axis, along y-axis. Okay? Now, having said that, let's also look at, if you choose to test your relationship of charge Q with columns. So you rearrange the equation in such a way that you have Q is equal to VC. Then you plot the graph of Q against different values of C. Then at this point in time, your slope will be equal to V, which is the applied voltage. And with this, you will have your change in Q over change in C as what will give you the value for your V, the applied voltage. I want to believe you are following. So I go on very quickly. I believe you are following.
Yes, sir.
Great.
Yes, sir. Yes, sir.
Okay. So we continue. The capacitance of a capacitor is a measure of the amount of charge a capacitor can store, and is actually determined by the capacitor geometry as well as the dielectric between the plates. I will explain that very quickly to you. Now, we had said earlier, the capacitance of a capacitor is a function of the capacitor geometry. What do we mean by capacitor geometry? The construction of your capacitor. What type of plates do you have in place? Is it a rectangular plate, or a square plate, or a circular plate? Depending on the type of plate you have there, that is what would determine what will make up the area of the plate. If your plate is a rectangular plate, the area of the plate will simply be given as length times breadth. If it's a different type of shape, the shape of the material would determine the area of that particular plate. That's a factor that contributes or constitutes to the capacitance of a capacitor. Another one is the distance between the plates. The distance between the plates is part of the geometry. How wide are these plates from each other? Are they so wide from each other? Are they so close to each other? This will also contribute to the capacitance of that capacitor. And another factor that will also contribute to the capacitance of a capacitor is the dielectric material between the plates. Now, there are different kinds of dielectric material that we will see very shortly. So this is also another factor that determines the capacitance of a capacitor. For a parallel plate capacitor made up of two plates of area A and is separated by a distance D with no dielectric material, the capacitance of that capacitor is given as C is equal to epsilon naught A over D, where your epsilon naught is the permittivity of free space, and it has a constant value of 8.85 times 10 raised to power minus 12 farad per meter. And your A, as mentioned earlier, is actually talking about the area of the plates that makes up the geometry of the capacitor. And D is the distance between the plates, which is also part of the geometry of the capacitor. So you can see the area of the plates as well as the separation is the major determinant of the capacitance of a capacitor. If you look at this equation very closely, we can say that C has a one-to-one relationship with area A. By implication, there is a direct proportionality between C and A. When area increases and epsilon naught and D remains constant, the capacitance of capacitor will obviously increase. Do you agree with me? I want to believe so. And there is an inverse relationship between capacitance and the distance separating the plates. So if in this case I assume that my epsilon naught is constant and A is constant, then I can say C is inversely proportional to D. And the implication here is this: when the value of D increases, the capacitance of capacitor will decrease because there is an inverse relationship between them. So take note of this, that the capacitance of capacitor is measured in the units of farads. And the symbol is F, farads, F. A 1 farad capacitor is exceptionally large. So in most cases, the capacitance of capacitors are either measured in picofarad or microfarad or nanofarad. I believe you are familiar with that. Picofarad is 1 times 10 raised to power minus 12 farad. Picofarad is 1 times 10 raised to power minus 12 farad. Nanofarad is 1 times 10 raised to power minus 9 farad. While microfarad is 1 times 10 raised to power minus 6 farad. So you need to get familiar with this when you come across capacitance expression and their units, as the case may be in the course of your study. So let's quickly go to dielectric material in a parallel plate capacitor. Dielectric material in parallel plate capacitor. So when we talk about dielectric material, we're talking about insulating material that is placed between the plates of the capacitor. Dielectric materials are insulating material, non-conducting material that is placed between the plates of the capacitor. And this causes the electric field inside the capacitor to be reduced for same amount of charge on the plates. Of course, if there's an insulating material, definitely the field that is usually set up within the capacitor will definitely be affected by this insulating material. So this is because the molecules of the dielectric material get polarized in the field, and they align themselves in a way that sets up another field inside the dielectric opposite to the field from the capacitor plates. So in essence, when you have dielectric material in between the plates of a capacitor, definitely the capacitance of that capacitor will be different from a situation where you don't have any dielectric material between this capacitor. And so we quickly move on, and we look at the dielectric constant. K is the symbol for dielectric constant, and it's actually the ratio of the electric field without the dielectric to the electric field with dielectric. Usually, when you apply a potential to a parallel plate capacitor, in between the plates, electric field is set up. I repeat, when you apply potential voltage to a dielectric material, to a capacitor, electric field is set up between the plates. And when you also place a dielectric material in between these plates, that's also set up electric field. However, the electric field that is set up as a result of the dielectric that is in between the plates will cause polarization of the dielectric material you place in between. And so we have the we have the electric field without dielectric material, and then we have the electric field with dielectric material. Is that okay? And the ratio of these two is what gives you the dielectric constant of that material. And if you look at this place, for free space, the dielectric constant is equal to 1. Why? Because if it's free space, meaning the electric field with dielectric will be equal to electric field without dielectric. And the ratio of that to ratio of one to the other, we gave you 1. Hence, for free space, we have dielectric constant to be equal to 1. However, if we have air, I believe you know there's difference between free space and air. Air is not a free space. Air has constituents. You have several gases that constitute air in different proportion, different percentage. Is that okay? So if you have air in between the parallel plate capacitor, the dielectric constant is given as 1.0006. It's approximately equal to 1 as in free space. Then for glass, we have dielectric constant to be equal to 6, and for water, dielectric constant is 80. Okay? Let's also look at
space.
Go ahead, please.
Sir, how can you get free space?
How can you get free space?
Yes, sir.
You can get free space by creating a vacuum. You create a vacuum. You need an enclosure. If you have an enclosure that is airtight, then all air inside can be sucked out. Then you have a vacuum inside. So that is how to create a vacuum. I don't know if you have heard of vacuum tubes. Is that okay? Or vacuum diodes. That is the way they are created. You create a vacuum inside a glass where no air is present at all. It's completely empty. So you can create a vacuum. Is that okay by you? Is that okay by you?
Yes, sir.
Okay, okay, good. Now, just take a look at this. This is a parallel plate capacitor. This is positively charged plates, negatively charged plates. These are the lines of electric field that is set up within these plates with no dielectric material between the plates. And this is the distance separating these two plates. Is that okay? However, when you introduce dielectric material in between these plates, then you have this A0, which is the electric field that has been reduced between the plates as a result of the dielectric material, which is polarizing itself within this material. You have positive, negative being created within this place. Is that okay? And so you have the proportion of A0 over E, which will give you the dielectric constant. Okay? Now, for parallel plate capacitor, electric field is usually computed or calculated as the ratio of voltage, applied voltage, divided by the distance separating the plates. Now, let me quickly say this. Field will not be set up within the plate except there is an applied voltage. Is that okay? And the field that will be set up will be the ratio of the applied voltage divided by the distance, and it will have a unit of volts per meter. Volts per meter. That's the unit of the electric field, volts per meter. Okay? Then the capacitance of capacitor for a capacitor with dielectric material is given as C is equal to K epsilon naught A over D. Remember, in a free space, K is equal to 1. So you will have your C like we had earlier as epsilon naught A over D. I believe you are with me. Okay? So let's quickly look at the energy that is stored in a capacitor. The energy stored in a capacitor is given as, sometimes it's given as U, or you can see it as E sometimes, but I use U here. Is given as half QV, or half CV square. Half QV or half CV square. If you bring your expression of Q is equal to CV to replace this, you get half is equal to CV square. Is that okay? You can also express it the other way. If you substitute, you have Q is equal to CV. So you can actually express it in terms of Q and C as well. Is that okay? You have expressed energy in terms of Q and V here. You have expressed it in terms of C and V here. You can as well express it in terms of Q and C by simply substituting it with the expression from Q is equal to CV. Okay? So lastly on this, let's quickly look at other uses of capacitors. Capacitors are used in computer memory. They are used in electric circuits for power supply, as filter, to be precise, in power supply. It's also used as a tuning circuit, and also used to minimize voltage fluctuations. Is applicable in flash bulb for camera flash or your mobile phone flash. Is that okay? Your camera flash releases a quantum of charge within a short time. Battery might not be able to deliver that. So because capacitor store charges and it can discharge it very fast, so it's quite relevant in that application. Okay. We had talked about this earlier, but we need to also look at it into detail and then draw some lines from its mathematics before we go to the simulation window. Okay. We had said that the capacitance of a capacitor is affected by the distance between the plates, which is D, and this is your D here. Are you following me, everybody? This is your D here. Okay. Are we together? This is your D. Okay. Then is affected by area of the plates. I've said that earlier. You have your area here. Is that okay? This is a constant, which is the permittivity of free space, and it has a constant of 8.85. times 10 raised to power minus 12 farad per meter. Okay, and then you have the dielectric material, which is this K. Is that okay? Is what also determines the capacitance of a capacitor. Epsilon naught is a constant. It doesn't affect the capacitance of a capacitor. Okay. So going further, we quickly have to now run the simulation, and let's see how we can actually implement some of these experiments. Is that okay? But before we go into this procedure, I will show you one more thing on this slide. Then we come back here. Okay. Yeah, let's look at this. We have done this. You've seen this earlier. Now let's quickly look at this. I have C is equal to epsilon naught A over D. Are we together? Without dielectric. Are you following me? By the time we compare this with a linear equation, by the time we compare this equation, let's pick this. I want to compare this with a linear equation. Are you following me? Do you agree with me? This is a linear equation. Do you agree this is a linear equation?
Yes, sir.
Okay, let's look at it from this figure now. It's linear because my epsilon naught A can be equal to M, which is my slope in this graph. And my C is what I have on my x-axis. And my D is what I have. Sorry, I have my C on my y-axis, and I have my 1 over D on my x-axis. So what is remaining in this graph, by the time you compare it with this linear equation, because there is no intercept, what we simply have left is epsilon naught A, which is equal to the slope of this graph. Does that make sense to everybody?
Yes, sir.
So we need to quickly go back to the simulation window, and as usual, we are making use of the Capacitor lab. It's a Java file, and it's available from the University of Colorado PHET simulation platform. You can actually click this link directly when you have the lecture material to download this. Okay, so I have this application downloaded on my system already, and so I'm just going to launch it. Then I will simply go ahead with what we have to do. Okay, this is my simulation. I'm going to share my screen with you very shortly so that you can see what I have. Can you see my screen? Can you see my screen?
Yes, sir.
Yes, sir.
Great. Good. So this is the Capacitor Lab simulation platform. We can actually look at about this simulation. It's actually powered by PhD Interactive Simulation with copyright 2004-2011, University of Colorado. And you have the version and the details. You can look at the credit of people who contributed to this. Is that okay? You have their name on this credit list. Okay, so I quickly close this. Now, you have 3 major tabs on this simulation platform. You have the introductory part, which is the one we're using today. You have the second tab with dielectric. You can see my dielectric. And then you have the third one, which is what? Multiple capacitors. Okay, so we're not going to use those ones today, so we are only limiting ourselves to this introduction today. Okay, now we want to perform a simple experiment based on the theory we have just talked about. Now, what was the theory? C is equal to epsilon naught A multiplied by 1 over D. Is that okay?
Epsilon.
We want to vary the we want to vary the value of D and measure corresponding capacitance. Then we'll plot a graph using Excel and see what our slope will look like. Is that okay? So according to the procedure you have there, you leave your plate area unchanged. Don't touch it. Don't change it. Let it just be what it is. So it's on 100 millimeter square. That's okay. So you don't change it. Is that okay? Then you vary the value. You vary the value of your D from 5 to 5.5 to 5.9 to 6.4 to 6.9 to 7.5 and to 8. One after the other. Then you will record the value of capacitance in picofarad and the value of charge in picocoulombs. I will show you how to do that quickly. So I quickly reduce this to 5 millimeter. Are you following me, everybody? So I have 5 millimeter already set here. By just moving this arrow, you can see 5 millimeter. That is my D, the separation between these two plates. And having done that, come to this place where you have meters. To the right view, click on electric field to show the field that is being set up, and then click on capacitance of the capacitor, and click on the plate charge. Is that okay? These are the 2 meters we need now to measure the capacitance of capacitor. And all you have to do, after you have been able to set this properly, all you have to do is to record the value of capacitance you have here. What value do you have here? Can I hear you?
0.18 times 10 minus 12.
Good. Times 10 raised to power minus 12 stands for what? Pico. I said that earlier. Pico is 1 times 10 raised to power minus 12. So you can either record it as 0.1 times 10 raised to power minus 12 farad, or simply say 0.18 picofarad, whichever one pleases you. Is that okay? Now, there is no charge.
Yes, sir.
There is no charge stored in this capacitor. Why? Because no electric field is set up in between the plates. And the reason is because no potential is applied to this capacitor. If no potential, no voltage is applied to a capacitor, no charge will be stored therein. And so you move this slider to 1.5 volts. Then you can see I have a value for my charge stored here now. You can reduce this meter so that it doesn't show up to the topmost bar. Is that okay? So I have 0.27 times 10 raised to power minus 12 coulombs. Is that okay? So that is the charge that is stored here. So go to your Excel and record what you have there. Let's go ahead. So you have 0.27 times 10 raised to power minus 12 coulomb. So you record that in your Excel table. 0.18, this is for picofarad. 0.26 you have 0.27 in your home case, so just change it. 0.27. Okay. Then you continue. The next value you are setting for your separation D is what? From this table, you are setting 5.5. So once you set 5.5, just move this slider slowly. You are excuse me, let me close this, remove this to make your work easier. Then set 5.4, 5.5. Okay, you set 5.4. Okay, set 5.4. Then display your capacitor. Then apply the voltage. Then you record the value 0.16, 0.24. You have 0.16, 0.24. Is that okay? So you continue until you record the last value. And once you have done up to the last one, which is 8 in this case, then you have a table like what I have here now. However, what graph are we to plot? We are to plot the graph of what? C in farad against what? C in farad against what?
D.
Is it against D? Against 1 over D. Good. So the next thing we need to do is to convert our D to meter to start with. Is that okay? If you are converting D to meter, the formula we use is this. Is equal to A2. I believe you still remember. A2 is picking this cell. Is that okay? Picking whatever value there. And is dividing it by 1,000. If you are converting millimeter to meter, what do? You divide by 1,000. Good. So that's what I have here. And so I can simply drag it and it will automatically compute for the rest of them. Okay? Then I want to convert my capacitance, which is in picofarad, to farad. If you had recorded your own with times 10 raised to power minus 11, great. But in this case, I put it as picofarad, so I'm converting it to farad. So what do I do here? I simply do B2, right? B2 multiply by 10 raised to power minus 12. Is that okay? So, no. Just a minute, please. 10 raised to power minus 12. Okay. B2, right? Times 10 raised to power minus 12. Now, let's go here and display more decimal places. Is that okay? So you have the value there. Are we together, everybody? So I drag the same thing and I have my capacitance recorded here now in farad. Now, I need 1 over D. So here, I need 1 divided by D. Is that okay? And in the unit of what? Meter raised to power minus 1. Meter raised to power minus 1. Okay? So, how do I do that one? I simply have this one to be equal to 1 divided by D, what? D2. Are we together, everybody? I'm taking reciprocal of D. I'm getting 1 over D. Are we together? So I have this and I drag it down.
Yes, sir.
Okay? So I have these 2 columns I want to plot. So I simply copy it. Then when I'm pasting it anywhere on this page, or let me click, open a new fresh sheet and paste it here. When I'm pasting value. Is that okay? So with this, I have this. However, your data has to be arranged in XY formats for you to be able to plot. Can you remember? And so, which one is my x-axis?
Yes.
Which one is my x-axis? It's 1 over D. And then my y-axis is this. So I need to move this to this side. Okay? Then the next thing is to select, and then I go to insert
Yes, sir.
chart. So I have my linear graph. And like you were taught, right click and click add trend line. Then select set intercepts, display on charts, and then you close. So by implication, I have my what? I have my slope to be equal to what? Can you say this? Let me make it a bit bigger. Can you see the slope?
No, sir.
You can say this.
No,
Let me
sir.
make it a bit bigger. Okay, it's bigger, bigger, bigger. Is that okay now?
Yes, sir.
So that is the slope of your graph. Is that okay?
Yes,
So
sir.
if you take the value of this slope from your graph and you equate it, are you following me? You equate it. Let's quickly do that one. This is 9 exponential. Let me get a place where we can quickly write. Okay. Okay. This is what we got. We have, so this might not be so fine, but we've got to make do with it. So if I have my epsilon naught over A, sorry, epsilon naught A is equal to slope. Do you agree with me? Do you agree with me, everybody?
Yes, sir.
Good. So epsilon naught is already known. Slope is already gotten from the graph. And so I can write my slope is 9 times 10 raised to power minus 16. Okay? Just don't mind. Okay, let me clean this. So 10 raised to power minus 16. Okay? Then you have your epsilon naught. You already know it. So you can have your A here and then divide this one by what? Epsilon naught. Is that okay? Are we together, please? By the time you bring in the value of epsilon naught and calculate, the value you will get for your area should be approximately equal to the value of the plate area here. And that will be that you've been able to verify that that expression is actually theoretically correct for expressing a capacitance of a capacitor. Are we together? So I go back to the slide and then I quickly take you through what you have to do. So you have the procedure to follow here, as I've just illustrated for you. And then you complete this table.
Sir, please come again.
Okay. What I'm showing you now is what I've just gone through. Is that okay? All these procedures, that's what I've just taken you through. And you will populate this table. Then you will also compute this other table like I've done just now. And then I've explained this earlier. I've explained this earlier also. And so that will be all for what you have to do. Then you can then follow these questions and save your work properly on your system. Now, for now, you are not submitting your report. However, whatever you will do in this practical, you have to keep it very well and keep your data intact, including your graph, because very soon, hopefully before next week or by next week, you will have to submit this on LMS. You will have to submit this on LMS. So I will make sure the video is released as soon as possible so that you can go over this lecture and master everything I've been able to, so that you'll be able to master everything I've been able to explain to you. And so on this note, I want to say thank you